All right, so we're going over some multiple choice questions from the first diagnostic test for the Kaplan AP Chemistry Review. So question number one, we are asked, we're given information where we have a solid sample of aluminum carbonate. And it's going to be strongly heated to drive off CO2. The CO2 is going to be bubbled through NaOH, which is going to form sodium carbonate and water. How many moles of NaOH are required to completely react with 0.60 moles of aluminum carbonate? So I think we need to take this one step at a time. So if we heat this, we will get 3 moles of CO2. Gas. And then we're going to have aluminum oxide.
Oh, sorry.
And if we look at this, we have a perfectly balanced equation, because every time we drive off a CO2 from a carbonate, there's one oxygen that's left over. So if we have 3 of them, that's 3 that's left over. We have 2 aluminums, we have 2 aluminums. And so now we need to react these 3 moles of CO2 with a certain number of moles of sodium hydroxide. And according to the question, this is going to produce sodium carbonate and it's going to produce H2O. So I really think the beginning portion is we need to balance this. And so we have 3 moles of CO2. So why don't we have 3 of these, which means we would need 6 of these. So the carbonate's taken care of. Now we need to worry about water. We have 6 hydrogens. Let's try 3 H2Os, and then we want to just make sure that all of our atoms are balanced. So carbon, we have 3, and we have 3. Oxygen, we have 6, 12. We have 9, 12. Hydrogen, we have 6, we have 6. So this is perfectly balanced. So for every mole of aluminum carbonate, I need 6 moles of NaOH. And I'm starting with 0.6 moles of aluminum carbonate, but they react in a 1:6 ratio. Therefore, I would need 3.6 moles of NaOH. And when we look at our answer choices, that is answer choice D for number 1. I want to skip ahead to question 3, and we are asked, under which set of conditions will a sample of gas deviate the most from ideality? So just a couple of things about the assumptions with the ideal gas equation. Number 1, we assume that there are no intermolecular forces. This means that we want atoms or molecules that aren't very polarizable, so we want small molecules. We want molecules that are moving, have enough kinetic energy such that they can't interact with one another. So for that, we want high temperatures. And the second assumption for ideality is that we have zero molecular volume. So what we want is to have the volume of the container to be much, much greater than the volume of the molecule. So when I have high temperatures and low pressures, because remember pressure and volume are inversely proportional, this is when a gas is most ideal. So the question is asking, which will deviate the most from ideality? Something that's large will be polarizable, which means it'll have more IMF. That violates rule 1. If I have a low pressure, not low pressure, but a low temperature, the molecules slow down enough so that IMFs become significant. An analogy I often use, if you are participating in a sport and you have practice and you're interacting too much with your friends during practice, coach can fix that by making you run faster. The faster you run, the more out of breath you are, the less you are able to interact with your friends at practice. So low temperatures would make IMF significant. And also if I had increased pressure, now that means that the volume of the container would begin to approach the volume of the molecule, which means I can't ignore the volume of the molecule. So these are the characteristics that we're looking for in molecules that deviate significantly from ideality. So we can eliminate B and D because those are small molecules. We know that we want low temperatures, so we can eliminate, again, B and D. And we want the pressure to be high, so we can eliminate B and C. That means that A is the best answer for number 3. So if we look at question number 4, we are asked which of the following explains why diamonds are hard and graphite is soft. The real difference between diamond and graphite is that graphite are interconnected carbon rings so I'm just going to draw a few of them to illustrate what a plane of these might look like. And then there's another plane of carbon rings but there is space between the planes of rings. This is why graphite is such a good lubricant, because literally these planes of rings can slide past one another. In fact, it wasn't that long ago that an issue of Science magazine did a study with a number of patients who had total hip replacements and found that the body naturally deposits graphite on the joint surfaces to extend the life of the implants. Diamond, on the other hand, actually has bonds between the planes of the atoms. That means it's more rigid and harder. So diamond is what we call a covalent network. You make a supermolecule, if you will. And what I mean by supermolecule is that you don't have intermolecular forces so much as you have intramolecular forces. So when we look at the answer choices, the one that really pops out to me is that diamonds have interlinked crystalline layers while graphite has flat planes of crystals. Statements like the carbon-carbon bonds in diamonds are stronger than those in graphite. No, they're not. A carbon-carbon bond is a carbon-carbon bond. The melting point of diamond is higher than that of graphite. That is certainly true, but it's true because it makes a super network. So that's not really an explanation. It is a true fact, but it's not a good answer. Diamonds are more stable than graphite. Certainly they are, but again, that's not an answer. C is an answer. C is a root cause that explains why statements like B and D are correct. Okay, now question 6 tasks us with finding the molarity of having 11 grams of CaCl2 and 100 milliliters of water. Now, calcium has a molar mass of 40.1. 2 chlorines has a mass of 70.9. Notice how nice that is. That is 111 grams in 1 mole. And so if I have 11 grams, for all intents and purposes, this is 0.1 moles in 0.1 liters. That's a 1 molar solution. So the answer choices I have are 5 molar, 9 molar, 0.9 molar cannot be determined. The best answer is 0.9 molar, which is answer choice C. Okay, question 7, we have ozone reacting with ammonia according to the equation that I have written at the top of the screen. When ozone decomposes in this reaction, the slowest step is actually when the ozone breaks apart. So that means that I can write the kinetic rate expression as the speed of the reaction is equal to K of the forward reaction times the concentration of ozone to the first power. This is what we call a dissociative mechanism. There's no collision, but rather it's a bond breaking process. So we're asked in question 7, how would the reaction rate change if the pressure of ammonia is doubled? This is very simple. Ammonia is not in the rate expression for the slow step, therefore it has no effect on the rate. If I were to double ozone, it would double the rate. If I were to decrease ozone by a factor of 2, the rate would decrease by a factor of 2. But ammonia is not in the slow step, so there is no effect. That is answer choice C on number 7. Okay, so now we're looking at question 8, and we want to be able to predict in a somewhat quantitative manner, but mostly in a qualitative manner, what's the pH of a solution that we make by combining 5 mils of 0.03 molar NaOH with 5 mils of 0.01 molar H3PO4. What I would do is convert these to millimoles. So I only have one hydroxide equivalent in every NaOH formula unit, if you will. So I have 15, 5 times 0.03 molar, and that's going to be 0.15 millimoles of OH minus. Plus, I am going to have, now here we have 3 equivalents of H plus, whereas this only had 1, but the concentration is 3 times less than it was with the base, but we have the same volume. At the end of the day, that's the exact same amount of millimoles of H plus. This is a strong base and a weak acid that is at the equivalence point. That means that when I neutralize, a lot of people would be tempted to say it's going to be a neutral pH, and they'd be wrong. Because the strong base contributes to the pH more than the weak acid does. So this is going to be an alkaline pH. Now you would expect something around maybe 8 to 9. I think that's probably a fair value. So our answer choices are strongly basic, weakly basic, neutral, weakly acidic. I would go with weakly basic. Strongly basic would be a pH of 12 to 13 to 14. So answer choice B makes the most sense. Okay, we look at number 9. We're given the following equation, and we want to identify the element that is being reduced, and then we want to identify the reductant. Okay, so the element that's reduced, first of all, it's got to be a reactant, so it cannot be CO2 and it cannot be NO. And we also need to identify not just the compound, but the element within the compound. So if we look at carbon, carbon in carbon monoxide is making 3 bonds to atoms more electronegative than itself. That is an oxidation state of +3. And in CO2, carbon is making 4 bonds to oxygen. That is an oxidation state of +4. The reductant the reductant is also the same thing as calling it the reducing agent, must be oxidized. So I know that CO is the reductant. So that eliminates answer choice A and answer choice C. What is reduced? Nitrogen has an oxidation state of +4. Each oxygen is -2. +4 to +2. That means nitrogen is the element that is reduced. So that means A is eliminated, and C is eliminated, and D is eliminated. So answer choice B is the best response for number 9. So we're asked in question 10 that if delta H is negative for a spontaneous reaction, what is true about the value of delta S? So I have a sign chart. This is one of 3 forms of Gibbs free energy equation. Delta G is negative for a spontaneous reaction. And there is one sign correction I need to make. The equation is delta H minus T delta S. So delta G can be negative, but I need very high temperatures. For the second criteria, delta G can be negative, but I need very low temperatures. The third set of conditions, this will never be negative. And for the fourth criteria, it will always be negative. Now it's asking us about delta S when delta H is negative. Delta H is negative in conditions number 2 and in conditions number 4. What can we say about the value of delta S? Delta S must be positive. That violates this premise, so we can eliminate A. Delta S must be negative. Violates this premise, so we can eliminate B. Delta S must be 0. Again, that's not supported by these mathematical facts. D, delta S can be positive or negative depending on the temperature. That is the best answer. D would be the best answer choice for number 10. Number 12 asks how many physically distinct isomers of dichloropropane are possible. So this is C3H6Cl2. So the C's have to be a chain. But I could put a Cl on one and also on one, and then hydrogens everywhere else. So that's a 1,1 dichloropropane. I could also do a 1,2. I could also do a 1,3. I could also do a 2,2. But there is no 1,3. So if you're thinking of this one, this is the same as this one. If I turn the molecule around and number the other way. So I could number this way, or I could number this way. So I see 1, 2, 3, 4 possibilities. This is a repeat. That is going to be answer choice D. So for number 13, we have a 0.1 molar aqueous solution of a white crystalline substance, and it shows a precipitate when it's treated with silver nitrate. That's a pretty important clue because silver nitrate is a soluble complex, but silver will make precipitates when I form it with lots of different things. So like with chlorides, bromides, and iodides, for one. Chlorides, bromides, iodides, for one. But also carbonates, sulfates, etc. Lots of complexes with silver are not soluble. And I want to write the answers that we're going to choose from. NH4Cl, K3PO4, KNO3, and NaCl. Now, when I treat this with silver nitrate solution, phenolphthalein turns pink, which means it's going to be alkaline. So what we want to look at is what all of these would be. So you would have AgCl, you would have Ag3, PO4, you would have AgNO3, which would make absolutely no sense. We can cross that one off immediately, because you're not going to make a precipitate when you make what you already had. It doesn't make any sense. And then, of course, AgCl again. So this is what I think they're describing. They're not choosing their words very well. I think they're not saying that when I reacted with AgCl3 that it turns phenolphthalein pink. Let's read it carefully. A 0.1 molar solution of an unknown crystalline substance shows a precipitate when treated with silver nitrate solution and turns phenolphthalein solution pink. That means that which of these would turn phenolphthalein pink? It would have to be number 2 or choice B, because this would make a weak base, this would make a strong acid, that would be acidic. This would be a strong base, this would be a strong acid, that would be neutral. This would be a strong base, this would be a weak acid, this would be alkaline. So on that basis, I would answer B. So let's talk about hydrolysis of salts for a moment. So I'm going to use answer choice A on our previous question. NH4Cl will ionize in solution to yield NH4 plus and Cl minus. But water will also ionize in solution. Not to a great extent, but it will, to make H plus and OH minus. I'm essentially going to have a double displacement reaction. So one of my products is NH4OH. Now we can use some criteria and determine that this is a weak base. And of course, H plus and Cl minus is HCl. And of course, we can use some criteria to show that this is a strong acid. The bottom line is the strong acid has a greater effect on the pH than a weak base. This completely dissociates, this one does not. Therefore, this is going to be an acidic solution when I dissolve ammonium chloride in water. And so you can go through that process for any salt to make those types of predictions.